Couple requests for homework problems for chapter 13. Anytime you're having trouble with them, let me know so I can kind of give you hints on these. Here's one. For me, this is number 18, but I have no idea. I think they're in random order. Okay, but it is an Arrhenius equation problem. It says a certain reaction has an activation energy of 67 kilojoules per mole and a frequency factor of 8.9 times 10 to the 12. What is the rate constant K? The temperature is 29. This one here is pretty straightforward. You're just going to plug these numbers into the Arrhenius equation and make sure your units are correct. So your Arrhenius equation here will be, here we go, K equals to A, which is your frequency factor, E raised to the minus EA over RT. Okay, so that's our equation. Let's write down all our data here. So we have activation energy, which is EA, is 67 kilojoules. So I have activation energy, 67 kilojoules per mole. R in this chapter is going to be 8.314, and that's joules, mole, Kelvin. T in temperature, let's see, this was given to us as 29 degrees Celsius. Okay, so first of all, all the units have to be like R. Do you see that R is in joules for one, and this is in kilojoules? So I need to convert this to joules. When you convert this to joules, you're going to multiply by 1,000. So it's going to be 6.7 times 10 to the 4th. And now that'll be in joules per mole, so that's good. And then this needs to be in Kelvin. Right now it's in degrees Celsius, so we need to convert this to Kelvin because R sets all the units. So we're going to add 273 to this. So we should get 302 Kelvin. Sorry. Okay, now let's plug everything into our formula here. You're going to do K equals to A, E, raised to the, I don't know why I'm rewriting the formula. Hold on. Let's plug everything in. So A, oh, I don't think I wrote down A. A was, hold on. Let's go see what A was. 8.9 times 10 to the 12th. Okay. A equals to 8.9 times 10 to the 12th, and that's molarity per second. And there's not a molarity and there's not a second in there, so those units are fine. Okay, so K will equal to A, which is 8.9 times 10 to the 12th. E raised to the minus EA. EA is 6.7 times 10 to the 4th. Divided by R, which is 8.314, times temperature, which was 302. So you just plug this into your calculator. This part right here, when I plug it into my calculator, let me rewrite all this, that equals to 26.68. Raised to the minus, and that'll be 26.68. So if you plug this part in, you should get 26.68. Now when I do E, let me see, E raised to the negative 26.68. So E, oops, and this is on your calculator. This is the second natural log. So it'll look like E to the X on your calculator, and that's the second natural log. Okay. So second natural log of negative 26.68. Oops. negative, sorry, I put in the wrong number, 26.68. I'll get it eventually. Okay, I get 2.58 times 10 to the negative 12. So K equals to 8.9 times 10 to the 12 multiplied by 2.5. We'll put 9 times 10 to the negative 12. And then when you multiply those together, K equals to, let's see, 22.9. Okay, so I hope that helps you on that part. Let's do the next part of the problem. And this could be, I mean, depending on how you rounded it, you could have gotten about 23. Anyway, so it's around 23. Let's do the next part of the problem. So again, that one is straightforward. It's just plug it into the formula. And the next part is a little bit more abstract. Okay, so it gives you the Arrhenius equation for a straight line, and it gives you all this information here, and it gives you data, and it says determine the activation energy, knowing that the slope is the negative EA over R. So let's see what we have here. Okay, so we know that slope, once we get that, equals to the negative activation energy over R. We know that R equals to 8.314 joules mole Kelvin. Okay, so we're trying to find activation energy, but first we need slope. And they gave us this data. They said that temperature equals to, let's see, we have a 352 and a 426. And we know that K equals to 109 and 185. Okay, so this is kind of like a T1, T2. This is like a K1, K2. Now, if we go back into algebra, if you're graphing a straight line, remember that equals to the rise over the run. Okay, so another way of saying this would be the change in your y over the change in your x. And again, another way of saying that, it'll be y2 minus y1 over x2 minus x1. Okay, and that's kind of like saying final minus initial. Now let's look at what our x and y are. Okay, so do you see that our y is natural log of k and our x is 1 over t? Just given to you, this is on the graph right here. So we have, come back over here, I know that when I graph my line, this, my y is natural log of k, and this, my x is 1 divided by t. So now I can plug that in. So my y will be, I don't have to say y equals to natural log of k, and x equals to 1 over t. So another way of saying this is natural log of k2 minus natural log of k1 divided by 1 over t2 minus 1 over t1. Okay, to find this is all equal to the slope. So let's plug it in our numbers here. Okay. Equals to, so I'll have natural log of k2, so here's my k2 right here, 185 minus natural log of 109 divided by 1 over t2, t2 is 426, minus 1 over t1, which is 352. Make sure you put your parentheses in correct for your calculator. Okay? And I'm going to kind of stop it at this point to make sure you can be able to do it on your own. Okay? But all you're going to do at this point, plug this in, okay, and you're going to get the answer for slope. Once you get that answer for slope, plug it into this equation right here. So we have R right here. We'll have slope once we get it right here. And you just find activation energy. And that's all you need to do there. Let me show you. Put it in the appropriate units. Remember that the R is in joules, so just remember that, and or to use the correct significant figures when you're doing this too. So I hope that helps get you started. Let me know if you need more help on this one.